So today I would like to speak about symmetries of 2+1D QFTs, particularly those implemented by topological line operators. And I would like to discuss a classification problem for these line operators and discuss some aspects of RG flows when such symmetries are involved. So this is based on this paper with Mahesh Balasubramanian and Matthew Buchan. So, so as a motivation, let's look at a scenario of an RG flow involving QFTs. So here I have a UV QFT with some invertible group-like symmetry. So there's a GUV is some faithfully acting symmetry of the UV QFT, and it has some anomaly. And we are considering some RG flow to an IR QFT, and in the IR, we can consider the faithfully acting symmetries of the IR QFT. And this group sometimes is a subgroup of GUV, sometimes it's not a subgroup, sometimes it's a much bigger group. And we can have an anomaly associated with the IR QFT. Now, we can have an RG flow, and when we have an RG flow which preserves the symmetry GUV, the symmetry GUV can act on the IR QFT. So that means that there's a group homomorphism from the UV group to the IR group. And it is not just an arbitrary group homomorphism, it is a group homomorphism which preserves the anomaly. So the anomaly matching condition tells us that the anomaly is matched under an RG flow. And we know that this is one of the strong constraints that we like to use to constrain possible IR phases for a theory given a UV theory and some symmetries. Now, in this setting, we would like to increase the tools that we have to have more symmetries, more anomalies, more invariants of an RG flow that we can potentially use to constrain the IR phase. So in this context, let us look at specifically about 2+1 dimensions. And let us look at UV theories which have topological line operators in them. So we can look at a UV QFT where you have some topological line operators, which I'm calling now BUV, which has some line operators, and the fusion rules of the lines may not be group-like anymore. We have some ring of fusion rules, some fusion ring determined by some integers. And we can again consider an RG flow to some IR QFT, where the IR theory also has some set of topological line operators. So similar to what we considered earlier, the RG flow defines some map between these topological lines. And again, we would like to study the anomaly for these symmetries because they will again act as some invariants for the RG flow and potentially helping us to constrain the IR phases. So identifying the anomaly of these symmetries, which are non-invertible symmetries, and identifying the anomalies for, let's say, BUV, can tell us about the possible IR phases. So that is the motivation for why we would like to understand these sets of topological lines and their anomalies. So this is the context in which I'll be motivating the classification problem that I will describe now. So there are various works on this, and which in 1+1D, in 2+1D, and even in higher dimensions. In this talk, I will stick to 2+1 dimensions and to topological line operators. So I will only consider topological line operators, but I will discuss some extensions to some other operators towards the end. So let me start with a bootstrap problem for these topological lines. So we would like to understand the basic data that describes topological line operators in 2+1 dimensions. So one basic data, so we can start with the set of line operators. And in this case, I will assume that we have a finite number of generating set of line operators. We have some finite set of line operators with particular fusion rules. And all other line operators can be constructed by direct sums of these line operators. So I'm assuming some finiteness here. And when we consider some ring-like structure like this, so we can start with our favorite set of some set here, and we can impose our favorite fusion rule by choosing some non-negative integers here. But unlike for groups, this may not be a consistent symmetry of a QFT. Given any finite group, we can write down some QFT with that symmetry. One trivial way to do this is to just consider the trivial QFT on which the group is acting trivially. And this is one of the trivial way to realize a group as a completely trivially acting symmetry. But nevertheless, we can write down a QFT with that symmetry. Even for non-trivial actions, we can write it down. However, when we choose an arbitrary set like this and some arbitrary fusion rule, it may not be a consistent symmetry of any QFT, because we want it to be implementable by topological line operators. So it should satisfy more constraints. So what is this extra data that we have? The extra data comes from crossing rules, because now we have some line operators implementing these symmetries. So the various ways in which we fuse the line operators are related by certain isomorphisms. So this is usually called the F symbols that describes the associativity of these fusion rules that we have here. Similarly, we are in 2+1 dimensions, so the lines can braid. So we also have a braiding, which relates these to the commutativity of the fusion rules. So this fusion rule is commutative, and at the level of line operators, we get an isomorphism between the vector spaces here at this junction. So together, we have the full set of data, the set of lines and a fusion rule, and these data must satisfy various consistency conditions, which are these pentagon and hexagon equations, and we often also require some unitarity conditions on these solutions. So this together describes a braided fusion category and a classification of symmetries, the finitely generated symmetries for 2+1D QFTs, in particular those implemented by line operators, is a classification problem which involves finding these solutions. So we choose our favorite fusion rules. We check whether there is a solution to these conditions. Sometimes there is no solution. Sometimes there are multiple solutions. So this is the classification problem that I'm interested in. So any questions at this point?
Did you say N is associative?
Yeah, so this fusion rule is associative and commutative.
Okay.
Yeah. So now let us look at some more data. So these FNR are the basic data that defines the data of these line operators. But we can also construct some more refined information, refined in the sense that this FNR are some matrices. Explicitly, if you write it down as a matrix, they obviously depend on a choice of basis on these vector spaces here. But we can also consider more basis independent data or more gauge invariant data, which can characterize line operators. And two such information is one is the spin of a line, which shows up in various ways. So in condensed matter, if you think of these line operators as world lines of particles, this spin is often referred to as the spin of an anion. So this spin can be a boson, or it can be a fermion, or it can even be an anion with a root of unity as its spin. This is one data. Another data is the braiding of line operators, these closed loops of lines, which gives us this S matrix. Together with the spin, this form the modular data because it's a representation of the modular group. And this S matrix will play an important role in my story, because this S matrix is like an anomaly for the line operators. And the reason why this is like an anomaly is because, first of all, one nice thing about the S is that the S doesn't depend on a choice of basis. It's a basis independent way of writing down these braiding. The braiding that we saw here, this depends on the basis, on a choice of basis, but S doesn't depend on a basis. But S in general has less information than the braiding, but nevertheless, this is a very interesting quantity to look at. And this is interesting because it tells you when two lines can detect each other under braiding. So that means that when you want to gauge line operators as symmetries implemented by a line operator, you don't want those symmetries to have non-trivial S matrix, because if two lines can detect each other, then you cannot trivialize both line operators. You cannot gauge both line operators, because gauging is trivializing the symmetry, but these lines can detect each other. So there's a mixed anomaly. So this S matrix, non-triviality of the S, is an obstruction to gauging the symmetries implemented by these line operators. So that's why it is this quantity will be very important in our discussion. Finally, I'll just mention a special case of the S matrix, which in my case will be just the invariant of one circle labeled by X, which is the quantum dimension of the line operators. And these quantum dimensions, they are a representation of the fusion rules. They obey fusion rule. So the quantum dimensions obey dx dy is sum on n xyz dz. So it's a very special representation of the fusion ring. It is very special because it's a in a unitary theory. This is the unique representation where all of these numbers are positive. So the quantum dimensions are a very special representation. And the reason why quantum dimensions are interesting is because quantum dimensions tell you when a line operator is invertible or not. So in this fusion rule, because the quantum dimension is a representation of the fusion rule, whenever the quantum dimension is 1 plus 1, we know that it's an invertible line operator, because whenever the quantum dimension is plus 1, there is always an inverse, and dx square is plus 1. So we can already infer from the quantum dimension whether a line operator has invertible fusion or not. And that will also play a role in our discussion. So this is some basic data about lines and their braiding. Any questions at this point? Okay. So let me go to some classification problems. So classifying these symmetries, which are one-form symmetries, because they are symmetries in 2 plus 1D implemented by lines. These symmetries, the general classification is very hard, because you can choose various kinds of fusion rings, and there are multiple solutions to the fusion and the braiding matrices. But there are some special cases where the classification becomes much easier. So what are some special cases that we can consider? One case is certainly when all the line operators are invertible. So in this case, we have a group-like symmetry. And in this case, the full data of the lines, their braiding, their associator, everything is determined by the spin of the line operators. So in this case, one can show that the spin is a phase for every line. So in this case, you have a group, one form symmetry group, and there is a quadratic form on the group valued in U1. So this spin actually completely specifies all the other data. So classifying these symmetries is a matter of choosing your favorite group, but this group has to be abelian, because the line operators fusion of line operators is commutative. And for an abelian group, we have to also choose a quadratic form, and this quadratic form will also tell you the anomaly of the one form symmetry. So this is the classification that one can do in this special case. Another special case is when the spin is 1. So this is not the same as the previous case. In this case, we do not assume whether the line is invertible or not. The line can be non-invertible, but we assume that all the line operators that we are considering are all bosons. So we don't want fermions or anyons. All of them are bosons, and they are all closed under fusion. We have a set of lines closed under fusion, and they are all bosons. In this case, again, we have a classification. Such a set of lines, such a braided fusion category, is a representation category of a group. So given it is always of this form. So given a group, we can write down Wilson lines labeled by representations of irreducible representations of the finite group. And the fusion rule is given by the tensor product of representations, and the associator and the braiding are all come from the data of the representations. So in this case, we know that irrespective of a set of lines that we start with, as long as they are closed under fusion, and as long as their spin is always 1, it is always representations of some group. And there is some group for which representations, their representation category is the same as what you started with. Now, this group here can be non-abelian. Here, there is no restriction on being abelian, because even for a non-abelian group, we know that the tensor product of representations commute. So this group here can be non-abelian. So this is another case where we can give a classification in the sense that at least this is in one-to-one correspondence with these representation categories. So given these two cases, a natural next step is to consider a classification when the spin is plus or minus 1. So that means what happens if the set of lines that you have are both fermions and bosons. Suppose you have a set of lines closed under fusion. They are fermions and bosons. If it is completely bosonic, this is the answer. But what if there are some fermions? What is the general structure of such symmetries? So this is the main content of this talk, and I'm calling these bosonic and fermionic one-form symmetries because, as is clear, the spin of these line operators are plus or minus 1. That is why these are called bosonic and fermionic one-form symmetries. So this would be the main question. So why are these symmetries interesting? So as we saw, it's a natural next step in the classification based on the spin of the line. And another interesting scenario is again involving an RG flow. Suppose you have a UV QFT with a set of line operators where all line operators have spin plus or minus 1, so real spins. Now you go through an RG flow and you get an IR theory, and you have some IR set of line operators in the IR theory. And the question is, can the IR line operators, can it have some anionic line operators? So in the UV, you started with a set of lines which are not anionic. You have bosons and fermions, but you go to the IR, and the question is, can the IR theory have some emergent anionic line operators? And the point is that this can often happen, and in many cases, it's actually required that you should have such anionic line operators in the IR. So even if you start with a UV QFT with line operators with real spin, often in the IR theory, you will get line operators with complex spins as emergent symmetries. Okay, so this is the main, so this concludes the motivation of why I'm interested in these symmetries. So any questions on this? Okay. So let me look at some examples. So whenever you try to classify some special type of topological operators, it is easiest to look at TQFTs with the same property because TQFTs are more constrained than the line operators in a general QFT. So you can first ask about TQFTs with the same property. So what are some examples of TQFTs where all line operators are bosons or fermions? One example is the Z2 digraviton theory in 2 plus 1D, where you have 4 line operators, 1, E, M, and psi. You have 3 bosons and 1 fermion. So this is an example which satisfies the type of line operators that I'm talking about. So this is an example of a QFT, in this case a TQFT, where the entire symmetry or all the line operators have real spin. Another example is this 3 fermion model or spinate at level 1 Chern-Simons theory, where you have a bunch of fermions. So you have the trivial vacuum and you have 3 fermions. And this is also another example of the kind that we are looking at. So this is the digraviton theory, and this is a 3 fermion case. So the claim is that any spin TQFT, so this is an arbitrary TQFT now, any spin TQFT with bosonic and fermionic line operators. So all line operators are bosonic or fermionic. Any such TQFT is always of this form. So you have some copies of E2, where E2 is this theory here, some copies of F2, where F2 is this theory here, and you can have an SVEC. So SVEC is just a fermionic line. It's an order 2 fermionic line operator. So this is the general structure of any TQFT with only bosonic and fermionic line operators. Now you look at this theory, and you can see that this is a theory with only invertible line operators. E2 has only invertible line operators. F2 only has invertible line operators. And this SVEC is an order 2 fermionic line. So all line operators here are invertible. So that means that if you have a TQFT with spins, real spin, line operators with real spins, such a TQFT necessarily has only invertible line operators. So that is a huge simplification, right? Such a TQFT only has invertible lines, and then it's a question about what are the invertible TQFTs with invertible lines with this property. So you can reduce this classification problem to TQFTs in which all line operators are invertible. Okay. So how does one show this? So with the right ingredients, the argument is very easy. So you have assumed that all line operators have spin plus or minus one. Then you can look at the braiding that we looked at. The braiding has an expression in terms of the spin and the fusion rules of the line operators. Now, when the spin is real, then you see that the braiding is also real. All components that show up here, the fusion coefficients, the Conan dimension, the spin, and this is a normalization factor, which is also real. So the entire S matrix is real. In general, it can be a complex matrix, but in this case, it is real. But the S matrix is also a unitary matrix. So that means that the square of the S matrix is the identity matrix in this case. So the square of the S matrix is the charge conjugation matrix. The square of the S matrix tells you when relates a line operator with its conjugate line. So a line and its orientation reversal. So these two line operators are related by the charge conjugation matrix. But the S matrix being real means that the charge conjugation matrix is the identity matrix. That means every line is its own dual. So every line is its own orientation reversal. So that means that we have a self-duality under every line is self-dual. That means that you can have these junctions, these trivalent junctions for lines. So you have A, and then the trivial line coming out. This is consistent only when a line A is self-dual, but this assumption implies that all lines have this junction. Once you know this, then you can define certain properties of these line operators. So you can look at a junction like this, where you have A coming in from the left, A coming in from the right, and then you have the trivial line coming out. So this junction, you can deform it in this way. You can put an S shape. Or in other words, you can start with an S shape and you can straighten it out to a straight line. However, this straightening out is not a trivial process in general. And there's usually an anomaly associated with it, or a number associated with it. You cannot straighten lines out for free for topological lines. And that is because of the associator that you have. This diagram here is related to this diagram through some F moves. And if certain components of the F matrix is non-trivial, then this operation of straightening out this S shape is non-trivial. In particular, it is known that the relation between this diagram here and this diagram is just a sign. It's a plus or minus one sign, and it is often referred to as the Frobenius indicator, because it's like the Frobenius indicator for representations of a group, which tells you about real representations versus complex representations. And this Frobenius indicator is the quantity that relates the spin to the fusion rules, because the Frobenius indicator in general is some associator, but in special cases you can write down an expression for the Frobenius indicator. So this is for a TQFT. This is only true in a TQFT, this expression. You can write down an expression for the Frobenius indicator, and here you can see that this is all the basic data that we already defined for the line: the spin, the Conan dimensions, and there are some this R matrix for the line operators. The second sum here is a sum over lines which are transparent. So these are lines which braid trivially with all the other line operators. So in a bosonic TQFT, this part is completely trivial because there are no lines which braid trivially with all the other lines except the trivial line. So this is a sum over non-trivial lines which braid trivially with all the other lines. So for a bosonic TQFT, you can completely forget about this part. For a fermionic TQFT, in principle, this part can be non-trivial. But again, it turns out that this part can be set to trivial, can be ignored for the particular computation that we are interested in. So basically, you have an expression where what is really relevant is this part of the Frobenius indicator. And you can see that it's quadratic in the spin. So that is why this quantity is the right thing to study, because the Frobenius dimension is quadratic in the spin. And therefore, when the spin is real, this whole part simplifies dramatically. In fact, you can show that when the spins are real, the Frobenius indicator is equal to the quantum dimension of the line operators, because this part becomes 1 plus 1, and this sum of quantum dimensions, you can simplify it to a single quantum dimension, because the quantum dimensions are representations of the fusion ring. So it satisfies the fusion rules. So you can show that the Frobenius indicator is actually equal to the quantum dimension. But we already know that the Frobenius indicator is actually plus or minus 1. So that means for consistency, the quantum dimensions should be plus or minus 1 for all line operators. Now, this is where we use unitarity of the TQFT. If the TQFT is unitary, then the quantum dimensions must be positive. So then that tells us that the quantum dimensions are actually plus 1. So this is how we go from the statement that the spin is plus or minus 1, all spins are plus or minus 1, to the statement that the quantum dimensions is plus 1. So quantum dimension being plus 1 then tells us that the line operator is invertible. And this is true for all line operators. So all line operators are invertible. So questions on this proof? Okay. So then what we have shown so far is that if the line operators are all have real spin, then all line operators are invertible. So that means that the classification is a classification about these invertible TQFTs with invertible line operators, and they have been completely classified as we saw earlier. So we can just use that classification result of TQFTs with invertible line operators, because these are also Chern-Simons theory with abelian gauge group. They are the equivalent. So you can look at all possible Chern-Simons theory with abelian gauge group and just look at those which have real spins. And that is how you can write down this general statement that any such set of line operators that we have is actually given by this particular theory. Because if you look at the classification, you'll find that these are the only theories with real spins. So this is how we can show this. Now, a crucial ingredient that we used is unitarity for the theories. And that is crucial because if the theory is non-unitary, if you have a non-unitary TQFT, then if the quantum dimension is plus or minus 1, it does not imply that A is invertible. So this is only true for unitary TQFTs. But nevertheless, you can use a similar argument even for non-unitary TQFTs. So it is this argument that I gave in this talk now depends on unitarity, but you can sidestep it. So this is a statement which is true for general TQFTs, non-unitary ones also, and also valid for spin TQFTs. So it can be bosonic, fermionic, or unitary or non-unitary. You can give a alternate proof, which is not very different from this for the non-unitary case as well. Okay, so what are some consequences of this statement? So as I said, if all line operators in a TQFT have real spin, then we have invertible fusion rules. So what is the converse of this? The converse is that if you have non-invertible fusion rules, then the line operators have complex spins. So that is the converse of the statement. What does it mean more physically? Suppose you have a topological phase, which you assume that the low energy theory or the excitations of that theory is described by a TQFT. Then you can apply this theorem to that topological phase. And what is the statement at the level of anions? What you have shown is that anions, suppose you have a system of anions with non-abelian fusion rules. So that means that, which is the statement in the low energy case, when you say that line operators are non-invertible, for the anions, it means that the anions are non-abelian. So if you have non-abelian anions, it implies that you have anions with complex spin. So This is basically a way of saying the same thing, but for quasi-particles on in a topological phase. So this shows that whenever you have non-invertible, non-abelian anionic fusion, you always have some anion in the system which have complex spin. And this is a statement which is true for any TQFT or any topological phase, as long as the low energy limit is described by a TQFT. So that is a consequence of this classification. Another consequence that I would like to highlight is about symmetries of TQFTs. So if you look at symmetries of TQFTs, so these are, now I'm talking about zero form symmetries. That means we are in 2+1D, so these are symmetries implemented by surface operators. So surface operators are acting on lines, and the lines are getting permuted under the action of the zero form symmetry. And if you have unitary symmetries of a TQFT, they can permute the line operators, but they may not permute the line operators. You can have non-trivial symmetries of a TQFT which do not permute any line operators. But then why are they non-trivial? Because they can act on the junctions of the lines. So these are some very special symmetries which do not occur in simple TQFTs. These are symmetries which do not permute line operators, but can still be non-trivial because they act on the junction spaces of the lines. Such a scenario cannot happen for time reversal symmetries. When you have time reversal symmetries, it acts on the lines to change the spin. So a time reversal symmetry, when it acts on a line, it complex conjugates the spin of the line operator. So another consequence of the classification is that in a non-abelian TQFT or a TQFT with non-invertible line operators, you necessarily have line operators with complex spin. So that means that if such a TQFT has a time reversal symmetry, it can never act trivially on the line operators. So that means you can always detect time reversal symmetries at the level of the line operators. You don't have to go to the junctions of the lines. This is in contrast to unitary symmetries, where Davidoff, for example, has explicit constructions of unitary symmetries, which act completely trivially on the line operators. So that doesn't happen for time reversal symmetry. So that's another consequence purely for TQFTs. Okay. So far we looked at TQFTs, some classifications of TQFTs and some consequences for TQFTs. But what we are really interested in is a general question about line operators in a general QFT. And of course, in that case, you don't have all of these constraints on the line operators that we have used so far. So we would like to classify line operators which can show up in a general QFT, but again with real spins. So what is the structure that they have when you try to look at their anomalies? But the point is that this TQFT classification is enough to also classify them. And I will explain why that is the case in the next slide. So suppose you have a set of line operators in a QFT which can braid again through the S matrix. In a TQFT, the special thing is that there are no transparent line operators. Every line braids non-trivially with some other line. However, in a QFT, this is not the case. You can have transparent line operators in a QFT. So how do you know whether something is a TQFT or a QFT? For example, at the level of the line operators is that you can ask whether this matrix is invertible or not. For TQFTs, this matrix is invertible. For generic QFTs, when you look at a set of line operators, this matrix is not invertible in general. Okay, so if this matrix is invertible, then the lines form a TQFT. If this matrix is not invertible, it means that you have a set of transparent line operators. So let Z of B be the transparent line operators in B. So these are set of line operators that are transparent. If S is not invertible, you are guaranteed to have at least one non-trivial line which satisfies this. So this is a set of lines so that the S matrix is just given by the quantum dimension. So what does this equation mean? It means that if you have a link of two line operators, you can unlink them without any cost. So that is this equation here. So this Z of B is a set of line operators which braid trivially with all the other lines. So that is this set of line. So if something is not a TQFT, this set is always non-empty. Well, this set is always contains the trivial line, But I'm saying that this set always contains a non-trivial line if it is not a TQFT. Okay. So given B, which has a non-trivial ZB, the ZB contains line operators which braid trivially with each other. That means that this ZB is actually a non-anomalous one-form symmetry because there is no mixed anomaly between the line operators. They all braid trivially. So you can gauge these line operators. So given B, you look at ZB and you gauge ZB to get a new set of line operators. So you started with B, which may have some transparent lines. You gauge away the transparent lines to get something which do not have any transparent lines because you have gauged all the transparent lines that you have in the original set of line operators. That means that when you gauge all of these line operators, you get something which is a TQFT because now this doesn't have any line operators which are transparent. So this M is a modular tensor category. So in the categorical language, B is a braided fusion category or a braided tensor category, which can have some transparent lines. You gauge all of them to get a modular fusion category. So M is a TQFT, and I will refer to as like the parent TQFT of B. So starting with any B, you can go back to a TQFT. So that is one step. Now, how do we use this? Well, we invert this process. What we learned is that if you start with any B, we can always gauge away the transparent lines and go back to a TQFT. But this is a discrete process. You can invert it. So that means that any B can be constructed from a TQFT by gauging some symmetries. That is the opposite problem. So here you are gauging a one-form symmetry. So the inverse process is gauging a zero-form symmetry. So you can construct the possible B, various types of categories by starting with a TQFT and gauging some symmetries. So that is the point here. So if S is invertible matrix, then the lines in B is already a TQFT. And if the lines in B have real spin, we have already classified them, these TQFTs, which are all E2 to the some power, this F2 to some power, and some SVEC. So it's a very simple description of such TQFTs. If S is non-invertible, then there are transparent lines and you gauge them to construct a TQFT. But then this TQFT doesn't have lines with complex spin. You started with B, in which all lines have real spin. You gauge away the transparent lines. The resulting M, this modular tensor category, again only have lines with real spin. That means this TQFT M, this parent TQFT, is also of the kind that we talked about, that we classified already. So that means that you can start with a TQFT of the kind that we already classified, gauge your favorite zero-form symmetry, and get a general set of line operators, which is a one-form symmetry in a QFT now with real spin. So any set of line operators with real spin can be constructed in this way. And the classification of such braided fusion categories is in one-to-one correspondence with a choice of a TQFT of the kind that we already looked at. So in this case, I'm assuming that there is no SVEC because I will focus the story on bosonic TQFTs. If there's an SVEC factor, there are some complications in the story. But assuming that you have a bosonic theory, you can start with any theory of this type, choose your favorite group acting on this theory, and you gauge that. You get a set of line operators with real spins again, and which can have some non-invertible S matrix. And any such symmetry is given by such gauging procedure. So this is the classification in a general for the general QFT, because a general QFT can have a general set of line operators of this type, but any such set of line operators always come from a TQFT of this type. Okay, so this is the main classification that I wanted to share. So any questions on this? Okay, so let us go back to RG flows now. So we have looked at a classification procedure that these symmetries are all coming from certain, these symmetries are all very special in the sense that if you require the spin to be plus or minus one, they always come from very special TQFTs. Now we consider some RG flows from UV to IR. And let me write down the RG flow explicitly in the following way. So suppose you have the UV symmetry BUV, and IR symmetry BIR. The RG flow tells me a line, how to map a line operator, a topological line operator in the UV to a topological line operator in the IR. I'm assuming that this RG flow preserves this BUV. That's why I can say that a topological line operator in BUV is mapped to some topological line operator in BIR, and that map can be written down in this way. So FRG is a map which takes a topological line operator X to a topological line operator in IR. But even if you start with a simple line operator, an indecomposable line operator in the UV, it can become a decomposable line operator with respect to IR theory. So that's why I have a sum of line operators. So this A is simple line operators in the IR. So a simple line operator in the UV, it generically can split into a sum of line operators in the IR. So this is a map. What properties should this map have? So this is not an arbitrary mapping of line operators. This is an RG flow. So we need to this satisfy certain very natural assumptions. One is that if you have a fusion of line operators, X and Y fusing to give Z, we want the image under the RG flow to have the same fusion, because fusion of line operators is a topological process. In particular, you don't really, these are the distance between these line operators do not matter, right? So that's why you are bringing them closer and closer to get a single line operator. So this process should not be depending on the scale that you are in. So this even if suppose you have a fusion of line operators in the UV theory, you can look at the fusion of line operators in the IR, the image of these lines in the IR, and you should get very natural fusion rules in the IR just following from the UV fusion rules. But this is not the full data of the lines, right? We already know that the lines have fusion, associator, and braiding. So we also need to specify what happens to the associator and braiding under an RG flow. To describe that, we have to tell what happens to a junction of line operators under an RG flow. Suppose you have X, Y, and Z. It's a junction of line operators in the UV. And each of these line operators becomes f of X, f of Y, and f of Z in the IR. So this is the image under the RG flow. When you go through an RG flow, the junction here, the junction of the vector space of operators here can also transform into its image in the IR theory. But this is a vector space. So these can be related by a invertible map in general. So that is why you have this extra data here, which tells you how to map junctions of line operators in the UV to junctions of line operators in the IR. Now you can use this map to then relate the associator and braiding of the UV and the IR line operators, because the associator and the braiding of line operators depend on the fusion spaces that you have. And this phi is something that comes from the RG flow. It's not something that we specify. If you know the RG flow, as an oracle, in principle, it is telling you how to map the operators in the UV to the IR. And in particular, it should also tell you how to map the junctions of line operators from the UV to the IR. And so this phi depends on the RG flow. And once you have the phi, then you can say how to relate F and R from the UV to the IR. So there are explicit expressions for how to relate F and R, which I will not go through, but one can derive, which is just using this phi. So mathematically, what you're saying is that in the UV, you have a braided fusion category. In the IR, you have a braided fusion category. And the RG flow is a braided monoidal functor between these categories. This is a natural generalization of what we saw for invertible symmetries. For invertible symmetries, we had a group in the UV, we had a group in the IR, we have a group homomorphism, which preserves the anomaly. That, a natural generalization of that to non-invertible lines is what I'm describing here. You have a map between lines which preserves the fusion rules, and it also specifies a map between the junctions so that the F and R, which are really the data that specifies all the anomalies, they are matched in a prescribed way. F and R are not invariant of the RG flow on the nose because they are basis dependent quantities. So they can change under an RG flow, but nevertheless, they change in a very prescribed way under an RG flow given by this phi. Now, computing this phi is very complicated, in a generic RG flow. Even for very simple RG flows, computing this phi is very complicated. I'm just describing the general structure. I will go to an example soon. Okay. So these FNR are not invariants of the RG flow because they depend on the fusion spaces. So what are the invariants of the RG flow? Well, one invariant is the quantum dimension. So the quantum dimension satisfies the fusion rules. And we saw that the fusion rule is preserved under the RG flow. Therefore, the quantum dimension is also preserved under the RG flow. More precisely, if you compute the quantum dimension of the IR image of a line X, which you can decompose in this way because f of x decomposes into some IR lines. So this is the quantum dimension of the IR line. This should be equal to the quantum dimension of the UV line operator X. So this is a statement which is at the level of the quantum dimension, and the quantum dimension doesn't depend on a basis. So this is an invariant of the RG flow. In particular, what does this mean? It means that if this dx is irrational, so suppose you have a quantum dimension which is irrational in the UV, then the IR cannot be trivially gapped. It cannot be a trivial theory because the trivial theory doesn't have any faithfully acting line operators. And in particular, you cannot have a line operator with irrational quantum dimension in the IR. So if the UV line operator, if you can find the UV line operator with irrational quantum dimension, the IR cannot be trivial. So this is a condition. And this is already known in 1 plus 1D. And the reason why this is true also in 2 plus 1D is because this relation here only depends on the fusion rules of the lines, and the fusion rule is a property for lines in both 1 plus 1D and 2 plus 1D. This doesn't depend on the braiding on the line operators. So because this is a statement that follows from the fusion rules of the lines, this is true in 1 plus 1D as well as 2 plus 1D. And these authors used this condition in various CFTs to argue for the IR phases of various CFTs where we have Verlinde line operators with irrational quantum dimension. Okay, so this is one invariant. Another one is the S matrix. So the S matrix already we know is something that is independent of the basis. So suppose you have a braiding of line operators in the UV. So X and Y are two line operators in the UV, which braid according to this matrix SXY. But this S matrix should also be preserved. And this is a formula that you can basically derive because, as I said in the previous slide, you can use phi to tell how F and R are related in the UV and the IR. And the S matrix is determined in terms of the F and R. So you can prove that this relation directly using the relation of F and R. So the result is that if you have a braiding of line operators X and Y in the UV, it should be given by this sum of braidings because each line operator X and Y goes to a sum of line operators. And for each constituent of the sum, you can then take the braiding. So that means the UV braiding of lines should agree with the IR braiding of lines, which is also very natural because again, the hop link or the braiding of lines, you can do it at whatever radius for the braiding. So the braiding of two line operators should not be something that changes under an RG flow. And that is precisely what this expression is telling you. Okay, so these are some invariants of RG flow. You can also describe other invariants, including the spin and other data. And in fact, to put more and more constraints on the IR phase, you need more and more invariants. This condition gives you some constraints on the RG flow, but if the quantum dimension is a rational number or an integer, this condition will not give you constraints on the IR phase. Because if this quantum dimensions are integers, you can have a trivially gapped phase as an IR phase. But however, even when these quantum dimensions are integers, the S matrix can still be non-trivial. So in that case, we might have some non-trivial anomaly, and therefore in that case, we already know that the IR cannot be trivially gapped because in a trivially gapped phase, again, we cannot have these lines matching the non-trivial S matrix. So that, and this is true for any lines, invertible or non-invertible. If the lines are invertible, then we will not have the sum. It's a direct statement that this S will be equal to this S. But when the lines are not invertible, you in general have the sum of sum over some S matrices. Okay. So let me give you, finally, let me give you a concrete example of this scenario. So the example is very simple. So you have a UV theory, which is this Dirac-Radhakrishnan theory coupled to a scalar field. So you have a real scalar field in 2 plus 1D. You have a Dirac-Radhakrishnan theory. Now, how do you couple these two? You consider a Z2 symmetry, which is acting on the Dirac-Radhakrishnan theory through its electromagnetic duality. So the Dirac-Radhakrishnan theory has two bosons. You have an EM duality, which permutes these two line operators. You can also consider a Z2 symmetry of the real scalar, which is just flipping the sign of the scalar field. So you can consider the diagonal Z2 symmetry, which acts on the E2, the Dirac-Radhakrishnan theory in this way, which acts on the real scalar in this way. And you can gauge this symmetry to couple these two theories together. When you gauge this Z2 symmetry, so this Z2 is a zero form symmetry. It is acting, it's a surface operator that is acting on line operators. E and M are permuted. It's a surface operator which is also acting on local operators. It's acting on phi and taking it to minus phi. So this diagonal symmetry you can gauge, and you can look at the resulting theory. If you gauge the Z2 symmetry of this scalar field with the TQFT, you get a theory with the following spectrum of line operators. So you basically have 1 plus 1 minus. What are these line operators? You have the trivial line in the Z2 discrete gauge theory, which is invariant under E and M permutation. So 1 plus is the trivial line. 1 minus is the one form symmetry dual to this Z2. So this Z2 is a zero form symmetry. 1 minus is an order 2 one form symmetry, which is dual to this Z2. These symmetries here, these line operators here, this is coming from the fact that the fermion is a fixed point under the EM duality. So that when you gauge the Z2 zero form symmetry, that line splits into two simple line operators, psi plus and psi minus. E and M form an orbit under the EM duality. So you get an orbit of E and M under gauging the Z2 symmetry. So that is why you have a non-invertible line operator when you gauge the zero form symmetry. So in total, you have all of these line operators. These are all invertible. This is non-invertible. You started with the Z2 Dirac-Radhakrishnan theory in which all line operators have real spin. So when you gauge the Z2 and go to a new theory, the resulting lines here also have real spin. These two have real spin. These two are fermions because they arise from the fermion psi in the Z2 discrete gauge theory. And this is again a boson because E and M are bosons. So this is a braided fusion category of the kind that we were classifying. So here we see that this comes from gauging a symmetry of a QFT coupled to a TQFT. So you have a QFT and a TQFT stacked together. You gauge a diagonal symmetry, and you get a general set of line operators. In general, you get a set of line operators, and if the TQFT that you had have only real spins, then the resulting set of line operators also have real spin. And this is an example of that case. This set of line operators is not a modular tensor category, and therefore this set of line operators do not form a TQFT. But this set of line operators do form a symmetry of a QFT. So the QFT is precisely these two theories coupled together under a gauging process. So in that QFT, this set of line operators sitting inside that QFT as a set of topological line operators, and this 1 minus braids trivially with everything. So that is why you know that it's not a TQFT. And this has a name, it's a Tambray-Yamagami category because these line operators are all order 2, and this is non-invertible. So it's a type of Tambray-Yamagami category, and this is how you can construct it through a usual gauging process in a QFT and that to a very simple QFT. Now, what happens under an RG flow? So in this case, we are interested in a very simple RG flow which preserves these symmetries. So we have 1, 1, minus 1, minus 1, 1. What is a simple RG flow that preserves the symmetries? Well, you can put a mass to the scalar field. So you put a mass to the scalar field and go to the IR. And when you go to the IR, the set of line operators that you have, these lines that you started with, BUV, all of them are preserved under the RG flow because you're just putting a mass to a scalar field, and they get enlarged to a bigger set of line operators. What is that set? It is icing times icing bar. So you have the icing TQFT. Just to remind you, the icing TQFT is a TQFT with three line operators in it, one, psi, and sigma, very much like the CFT, which have these spins, the boson, fermion, and an anion, and these fusion rules, like the primaries of the icing CFT. Now, icing TQFT is this TQFT. Icing bar is the same TQFT but complex conjugated spin for the sigma. So when you do this RG flow, you end up with this set of line operators. Now this is a TQFT. Okay, so this is a TQFT. Even though you started with something which is not a TQFT because it's a set of line operators sitting inside a QFT, you do this RG flow. In the IR, you get this icing time icing bar, which is a TQFT. And in particular, you get a sigma, which is an anion. You did not have the sigma topological line in the UV. It's an emergent topological line, which is anionic, which you didn't have in the UV. So this is what I meant initially, that you can get emergent anionic excitations. Even in this simple example, you can get emergent anionic excitations from the UV, even though the UV itself didn't have it. So the reason why you have this result is because, sorry, if you consider the Z2 discrete gauge theory without the scalar field, and if you gauge the Z2 zero form symmetry, this is precisely the TQFT that you'll get. So you start with the Z2 discrete gauge theory, you gauge a zero form symmetry, you get another TQFT, and that is this TQFT. And giving a mass to the scalar is like forgetting about it, right? So you initially had a scalar which is charged under the Z2 symmetry. So when you gauge, you do not get the full icing times icing bar symmetry. You only get a subcategory of the icing times icing bar symmetry. But when you put a mass to the scalar, there are some lines which are not topological, which become topological when you put a mass to the scalar. So there are some emergent symmetries in the IR, which is precisely this sigma. And there's also a sigma bar sitting here. So this is a very simple example where you can see that a UV symmetry gets enlarged to a bigger symmetry. The UV category was not modular because it was not a TQFT. But in the IR, when the IR is a gap phase, the line operators in the IR will be modular. So you are converting a non-modular category to a modular category under an RG flow. And in this specific case, it is called a minimal modular extension because this is independent of any RG flow discussion. This is just a statement that given any braided category, which is not modular, you can try to enlarge it into a modular category. And RG flows are physical scenarios where this naturally happens, where this enlargement naturally happens into a TQFT when the IR is gapped. Okay, so this is a minimal modular extension because this is the minimal way in which you can enlarge this set of line operators. So you can try to add new line operators into this set to make it a modular theory. And you can ask, what is a minimum set of line operators that you should add to the set of lines so that the resulting set of lines is a consistent modular category. And icing times icing bar is the minimal, the smallest such category. And in this case, you got a minimal extension when you go through an RG flow. But this is not always the case. In fact, there are categories which do not admit a minimum modular extension. So that is just my last point, that if you have a UV category, UV QFT with some category of symmetries, you may have a category which do not admit a minimal modular extension. In this case, if you have an RG flow and if the RG flow results in a TQFT, the TQFT must be a modular fusion category, even though you started with something which is not modular. So there is an extension happening, but that extension cannot be minimal because this category does not admit a minimal modular extension. So that means that the IR should have, not just that the IR should have emergent symmetries, it should have a minimum number of emergent symmetries for things to be consistent. There is a way of detecting when a category do not admit a minimum modular extension. So you can use, there's a criterion to check that. And whenever you have a UV QFT with such categories, you are guaranteed that if the IR is gapped, it must have a certain number of emergent symmetries. That is the only way to enlarge this category. Okay, so sorry. So that is the case with this minimum model extension. And sorry. So this is the, I will not describe the details of how to check this. This is explained in the paper. So let me stop with just showing you the conclusion, and please ask me any questions. Thank you.